Hi everyone, this is Akanksha and welcome to the third episode of our Mechanistic Interpretability 101 playlist. Today we are going to talk about calculus, and not only is calculus an important and fundamental branch of mathematics, but it also plays a key role in allowing the neural network models do the magic that they do. So let us begin understanding calculus. This has to be one of my most favorite memes. Are you also one of those who becomes this meme lady when you hear the word calculus? Worry not. We will try to understand the concepts of calculus and hopefully transition you into this reaction to the word calculus. So these are some of the fundamental branches of mathematics, and to put it poetically, these branches help us turn the chaos around us into harmony with every equation and allow us to dance with the mysteries of the world. So you know that algebra is the one that deals with arithmetics. Geometry is the one that deals with properties of shapes. So these two relations of algebra with arithmetics and geometry with shapes are clearly imparted in our minds. And even if we are asked about them in our sleep, we would be able to draw those relationships. What is calculus then? If you couldn't come up with a reply from this moment on, remember that calculus is the study of change. Was calculus trying to make us dislike it from the start? Didn't it know that humans hate the idea of change? Let us try to change this outlook about change today. In Latin, the word calculus means small pebble. Because such pebbles were used for counting out distances, tallying votes, and doing abacus arithmetic, the word came to be the Latin word for calculation. Now, on the earlier slide, we saw that calculus is the study of change. We will learn about this in detail. For now, just remember that calculus is divided into two main branches. One is differential and the other is integral. And we will learn how differential calculus is all about slopes, while integral calculus is all about area under the curve. If you're out mountain climbing, remember that the differential will help us know how fast we are climbing or descending a slope. And the integration will tell us about the total ground that we covered. So if you go and watch any other video on calculus or read any other material on calculus and try to learn about derivatives, most likely you will encounter the example of car and how fast it's moving and how much distance it has covered and how derivatives help us get this insight. But I wanted to use a different example. So I'm going to make this cute puppy serve us a plate of salad. So here in front of the puppy is a salad bowl. And as you can see, the pup is trying to add salt to the bowl. Now the puppy has no idea how much salt is perfect amount of salt for its human. So consider that it adds salt pinch by pinch and asks its human if the salad tastes good now. So the puppy is trying to learn math and wants to plot a graph of how the amount of salt changes the taste of salad. So then it puts the salt in pinches on x-axis and it puts the taste in percentages on y-axis. So as you can imagine, the puppy adds just one pinch of salt and the human feels the taste go up from 0 to 10%. Then the puppy adds 4 more pinches of salt. So now at 5 pinches of salt, the human says that they feel that the taste is almost 40% there. So now the puppy realizes that adding salt is helping and adds 4 more pinches of salt. And then at 9 pinches, human is happy to report that the salad is almost as tasty as it can probably be. So rates the taste to be 95%, as you can see here. The puppy wants to impress its human by making the salad taste 100% tasty. So then it adds 3 more pinches of salt, hoping the owner will like it even more. But sadly, the human says that the taste is a bit too salty now and reports just 90% taste. The puppy realizes that adding more salt is probably going to be a waste of an effort, but it is excited by the idea of plotting this graph of taste as a function of salt. So it adds more salt, and as expected, humans say that the taste is getting worse. And at 20 pinches, the human basically reports that the salad is completely inedible now with too much salt. So the human gives it a near 0% taste, as you can see here. So even though the salad is inedible at this point, the puppy is very excited looking at the peaks and valleys of this graph. It knows that there is a lot more to learn. The puppy aims to understand the secrets hidden in these curves. The concept of slopes is very important here. This part where the slope is increasing in the upward direction, where adding salt to the dish increases the taste, is considered a positive slope. Now look at this part that's going in the downward direction. Adding more salt to the dish here is going to gradually reduce the taste. So this is our negative slope. And this relatively flat part where the slope is neither increasing or decreasing, that is not going upward or downward, is the zero slope part. Adding more salt here does not have a significant impact on the taste. Now our puppy has wasted a whole bowl of salad just to plot this graph because it knew that plotting this graph would help it find the exact amount of salt in pinches that would lead to 100% taste. And the puppy knows that it doesn't want to waste time in trial and error, so it turns to math. Puppy wants to understand the effect of adding just a tiny grain of salt at a time and see how each grain addition changes the taste. The puppy realizes that the key to understanding how the taste changes with each grain of salt deals with instantaneous change. And so it knows that it has to look at derivatives. So when the puppy is trying to find the exact amount of salt corresponding to 100% taste, it is basically trying to solve this. Here f of x represents the taste as a function of the amount of salt x. And f prime of x here is going to be the derivative of the taste function with respect to salt. It tells you how the taste changes as you add more salt. By solving for f prime of x equal to 0, we are basically trying to find the value of x where the taste stops increasing and reaches its maximum value. This is the critical point that you're looking for to achieve the best possible taste. Puppy remembered that this is how the salt looks under a microscope. It knew that to find the impact of an infinitesimally small amount of salt, that is not even a whole grain of salt, it would have to use the concept of limits. Limits help us understand what happens to the function as the input gets closer and closer to a particular value. In this case, the puppy wanted to know what happens to the taste as it adds a minuscule amount of salt, which is almost zero, but not quite. So this is how we define limits in an equation. Here x is our input and a is the value our input x is approaching. So in our example, x is going to be the amount of salt that is approaching 0. So in this way, the derivative is all about understanding these tiny incremental changes. The smaller the change in the amount of salt, the more accurately the puppy can predict the taste. So let's leave behind the salty salad and eat some pizza now. So have you noticed that when you're hungry and you start eating pizza, initially you'll be very fast finishing the first few slices. But as you start feeling full, your speed of eating the slices is obviously going to reduce. So consider this example where the x-axis is time in minutes and the y-axis is the amount of pizza slices. So consider that in 1 minute you finish 1.5 slices of pizza. In 2 minutes, you finish 2.5 slices of pizza. And in 3 minutes, you're barely finishing 3 slices of pizza. So this graph is basically telling us the speed of eating pizza slices per minute. But what if we wanted to exactly calculate how fast we are eating pizza in each minute? That's where second derivatives come in picture. So if we had to plot the speed of eating pizza, what we get here is this. At 1 minute, we were able to finish 1.5 slices of pizza. But from 1 minute to 2 minutes, we were just able to eat one more slice. Because at 2 minutes, if you remember, we had 2.5 slices of pizza. So our speed of eating is reduced now. And at 3 minutes, we were just finishing 3 slices of pizza. So we just ate another half slice of pizza here. So this is basically describing the rate of change, and that's why it's called the second derivatives. This here is a list of common derivatives that are frequently used in calculus. Consider these as the fundamental rules that help us differentiate more complex functions by combining these basic derivatives with these different differentiation rules. So this here, the chain rule is one of the most important differentiation rules. The chain rule is crucial in machine learning because it enables efficient computation of gradients during backpropagation, allowing neural networks to learn and optimize complex functions. If you don't understand what exactly gradients and backpropagations are, don't worry, we will learn about all these concepts. Now let us understand the concept of partial derivatives using this multivariable function f of x comma y, which is equal to x square y. When we want to understand how this function changes with respect to one variable while keeping the other constant, we use partial derivatives. For instance, this is how we calculate the partial derivative of function f with respect to the variable x. It is denoted by del f by del x. We treat y as a constant here, and that's why using the constant rule, this is the answer that we get. And then we differentiate the function f with respect to y, and we denote that as del f by del y, which is going to treat x as a constant. And because we are treating x as a constant, this becomes just del y upon del y, which is 1. So that's why we get this answer. These partial derivatives help us understand the function's behavior in different directions, which is particularly useful in fields like optimization and machine learning, where functions depend on multiple variables. And now that we have understood partial derivatives, let's understand the chain rule. Chain rule helps us in differentiating composite functions. So if we have a function h of x, which is equal to f of g of x, then the chain rule tells us that the derivative h prime x is going to be equal to f prime of g of x into g prime of x. So let's look at this example to understand the chain rule better. Consider h of x is equal to 2x plus 3 raised to 4. So here g of x is 2x plus 3, which is the internal function. And if you consider this being equal to u, then f of u is equal to u raised to 4, which is what we see here. So using the differentiation rules, these are the values that we get for f prime of u and g prime of x. Now using the chain rule, this is the value that we get. So this is how chain rule helps us handle the derivative of functions nested within other functions. Now, whenever we start studying machine learning, gradient descent is the concept that's going to come up a lot. So let's try and understand what gradient descent means in mathematical terms. Before even going to gradient descent, let's understand what the gradient is. So the gradient vector del f here is a vector that contains all the partial derivatives of a multivariable function f. So for a multivariable function f of x comma y, the gradient is going to be something like this. The gradient vector points in the direction of the steepest increase of the function f. Each component of the gradient tells us how much the function f is increasing in that particular direction. That is, with respect to x and y here. So naturally, in gradient descent, the goal is often to minimize a function. And in case of machine learning models, this is going to be the loss function. So gradient descent is an iterative method to find the minimum point of a function. This diagram here shows the iterative process of starting at point x0 and calculating the gradient and updating the position by taking steps in the opposite direction of the gradient, so which is the downward direction in our case. This process is repeated, gradually moving towards a point where the function reaches its minimum value. So that was all about the differential part of calculus. Now let us move on to the integral part of calculus. Should we make this cute puppy do some more work for us? Imagine you have a large swimming pool in your backyard and you want to fill it with water using a garden hose. But there's a problem. The rate at which the water flows from the hose isn't constant. Sometimes it's high and sometimes it's low, depending on the water pressure. This flow rate can be represented as a function of time. So as you can see here, on the x-axis, we have time in minutes, and on the y-axis, we have water flow given in liters per minute. And because the water pressure varies, the water flow is going to be high sometimes and it's going to be low sometimes. So when the water pressure and thereby the water flow is in constant, it is not going to be easy to calculate how much water has been added to the pool over a certain period of time. And this is where integration comes into play. The integral helps us calculate the total volume of water accumulated in the pool over time, even when the water pressure is not constant. So in this plot, the function f of t is going to tell us how many liters of water has been added to the pool per minute. So as we can see from this plot, the water flow at the 4-minute mark is 25 liters per minute. So consider this small time duration dt around the 4-minute mark. And when we want to calculate how much water flowed in this time duration dt, we are going to get the answer 25 dt. So to understand how much volume of water accumulated in the swimming pool over the course of 0 to 10 minutes, we will have to add all these small dt values over the course of 0 to 10 minutes, and that's exactly what we do in integration. So the total water here is going to be given by this expression. Here this is the sign of integrals, and 0 and 10 are basically the starting and ending points. And this part here is basically the water flow rate as function of time into dt. So the water in interval dt around 4 minutes here was given by 25 dt. And similarly, for all these different dt values, we will have some water value. So basically, to find out the total water volume over the entire 10 minutes, we sum up all the water amounts over all these tiny dt intervals. And this summation or sum is nothing but integrals. So that's a wrap for this episode. We discussed the fundamental concepts of derivatives, and we understood the concept of positive, negative, and zero slope and what insights they give. And then we went on to learn second derivatives and partial derivatives and explored how the chain rule works and how the gradient descent works, and finally learned how integration works. I hope this video gave you a brief idea about the basic concepts of calculus. But understanding these concepts in detail is only possible when you actually solve the math. I'm going to link a Jupyter notebook in the description of this video where you'll see a lot of problems based on the topics that we discussed today. And solving those problems will help you grasp these concepts of derivatives and integrals and partial derivatives and chain rule much more in detail. So that's all for today. See you in the next episode. Bye.